So this presentation's on the Central Limit Theorem. It's about the distribution of the sample mean. This is in the OLI textbook. This is in Module 12. It starts on page 169 and runs through 172. And in the workbook, this is topic 6. Intervals and hypothesis testing. It's about if you take a lot of different samples, like everybody in the class has a different set of 36 counties, everybody gets a slightly different sample mean, and this theorem tells us how that is distributed. And we want to know because that will let us figure out the probability that whatever you get from your sample might be close to the truth. Now, in order to figure out what's the distribution of the sample mean, the x bar in general, what I want to do is to first just work on a particular example, and we'll see how it works out in this one case, and then we'll come to a general theorem that says it's basically going to work out the same way regardless what example you're looking at. But we're just going to look at this example with like a wheel of fortune spinner where you click this spinner and it spins around and around and comes to stop at a particular angle, x, between 0 and 360 degrees. And we're going to suppose this is a fair spinner so that all the angles are equally likely. And all the angles are possible, not just the whole numbers, but all the little fractions in between. So this is a continuous variable. And so one repetition of the experiment is to spin this thing once. But now you're going to get a sample of 36 repetitions, 36 spins or more. Well, we're going to start out with just a couple of spins and work our way up. And we're going to see what the sample mean distribution looks like. So just to recap, we're going to spin the spinner. We think the sample mean of the angle that we get, or the population mean of x, should be 180 degrees. We plan to test this by repeating the experiment n times and getting sample means. And we want to study the distribution of the sample mean. And the final answer to what this is will be the Central Limit Theorem. And that's going to tell us that we really get the same thing in all examples, not just this one. Now, let's figure out the distribution of the angle itself. All the angles are equally likely, so no part of the distribution should be taller than any other part. So there's a name for that. You call that the uniform distribution. If we made a histogram, all the bars would be equally tall. So I'm just drawing a horizontal line across there. And we think that's the distribution of x. How tall is it? Can you find the height k of the top of the distribution curve? What is it that we know about all distributions? Can a distribution just be any old function? No, it's a non-negative function, meaning it's above the x-axis. It has positive y. Okay, this does. And the area underneath has to be 1 or 100%. So this width here, 360 degrees, times the height, k, has to equal 100%. Area is 100%, width times height is 100%. The width is 360 degrees, so 360 degrees times k is 100%. So k is 5/18% per degree. So there's the shape of the distribution for spinning the spinner just once. Now, we want to work out the distribution of the sample mean for spinning it twice. So, the idea is we'd spin it twice and get the average. And then we'd spin it twice and get the average again. You get a whole bunch of these sample means for samples of size 2. And then make a histogram of them to see how they are distributed. Only right now we're not really spinning, we're making a theoretical model, a probability model for that. So, we're starting with small n, just 2 spins, and we're going to work our way up to what happens if you spin it many times. When you find the average of 2 spins, there are a whole lot of ways to get the average to be 180 degrees. For example, you could spin 179 and 181. You average those together, you get 180. Or 178 and 182. There are a lot of pairs like that that would average out to be 180. Okay. And not just pairs of whole numbers, but the fractions also. So since there's a lot of ways you can get 180, I'm going to put a dot on the graph above 180, and I'm going to think the distribution is pretty tall there. So I'm just going to mark that spot, and we can work out how tall later, but I want to work on the shape right now. So I want to get a few more points on the graph, try to see what the shape is looking like. Well, let's try 90 degrees. How many pairs are there that average out to be 90 degrees? See, you could have 189 and 191, or you could have 188 and 192, a lot of pairs again, but only half as many as before. You get down to the pair of 0 and 180, that could average out to 90, but that's as far as you go because you can't go below the 0. So there are half as many ways for the average to be 90 degrees. So above 90 degrees, I'm going to put a little mark that's only half as tall as the distribution was at 180. And the same goes for 270. And by the time you get 0 degrees, there's almost no way for that to happen. So there's the shape that you come to. Now, if you continue this, we need to see, we want to go to the next step. We want to go to the distribution of x bar 4, and then 8, and so forth. So, but the thing to notice is that the middle got pulled up and the edges got pushed down because there's more ways to average out in the middle than there are to average out near the edges. Okay. So now in this slide, we want to try to imagine the distribution of the sample mean for spinning 4 times. So the idea is you add up 4 spins and divide by 4, and that gets you x bar 4. And then another person could do the same thing, and another, and you take all your different x bar 4s and make a histogram of them. And in the bottom graph, which is empty right now, we want to fill this in with what we think the distribution is going to be. So now think about this. To add up 4 spins and divide by 4, it's the same result as if you did the average of 2 spins twice and averaged the 2 averages. It's the same arithmetic either way. So in order to get x bar 4, you're getting x bar 2, and then you're getting another x bar 2, and you're averaging 2 x bar 2s. Looking at the possibilities, there's twice as many pairs of x bar 2s that'll give you x bar 4 equals 180 in the middle as there are at 90 degrees. So there's twice as many of them that give you a mean in the middle as there is on the edges. And not only that, but the x bar 2s in the middle now are happening more often than the ones near the edges anyhow. So there's more pairs that average out in the middle, and the ones in the middle come up more often anyway. So now there's 2 reasons why the middle is going to be pulled up and the edges are going to be pushed down. Now, if you imagine this side of the distribution here as like a stick, just picture a ruler lying along there. If you were going to pull up in the middle and you're going to push down on the edges, that stick has to bend. And so you come to this. So we're already seeing the beginnings of an inflection point in the curve. Now the mean stayed the same. The mean of x bar 4 was the same as the mean of x bar 2. That was the same as the mean of the original x. It's all 180 degrees. The middle stays put. But the standard deviation is becoming smaller. See, the standard deviation here is smaller than the standard deviation there. Why? Because your average dude down here is closer to the middle, closer to 180 than the average dude up here. Because the middle values are more popular here than they were for x bar 2. It's like people out on the edges have sort of like walked towards the middle, made the standard deviation smaller. And now Gauss wrote an easy algebraic proof, just working with the formulas for the mean and standard deviation to show that what happens to the standard deviation is you divide by the square root of the sample size. And so the standard deviation of x bar n equals the original standard deviation of x divided by the square root of n. But Gauss's big accomplishment was to go further, and he didn't just work out the mean and the standard deviation. He worked out a formula for the shape of the distribution. as the sample size increases forever. And so what he showed was that regardless how x is distributed, the distribution of the sample mean approaches the normal distribution as the sample size grows larger. And so his big achievement was to find the formula for this curve that's being approached. And this is it. You don't have to memorize it. We're not really going to care exactly how tall the curve is anyway. It's not the y that we care about, it's the areas underneath. And we've learned how to work with Excel and some online applets and tables to figure out those areas already. The only thing you need to take away from this is that there's a connection to z. You see, well, first off, that once you know the mean and the standard deviation, that specifies the shape. So there's just two parameters for this distribution. And then the second thing is there's a connection to the z-scores. See that x minus mu divided by sigma, that's just z. Now the proof of this thing, we'd have to go well beyond calculus to do the proof. But just looking at the form of it, the thing to notice is that this x minus mu squared over sigma squared is z squared. And so that's why we're able to look things up in a standard normal table. If x was in degrees Fahrenheit or whatever, you just convert to a z-score, and then you can look in the standard. So I'll show you one more set of pictures on a single slide, just to show you how this works out when you start with a distribution that's not uniform. Okay, with the spinner, the distribution started out as a flat horizontal line, and then it became that normal bell shape as the sample size got larger. Well, here I'm not starting out with a flat horizontal line. I'm starting out with a distribution that's very bimodal. This is the data from our data sets spreadsheet. This is from the Old Faithful geyser example, where the geyser erupts in two different ways. It has two different modes of eruption. There are short eruptions, and then there are a lot of taller eruptions, longer lasting eruptions, but not very much in between, in the middle. And so if you start that way, the question is, as you take sample means with larger and larger samples, do you still approach this normal distribution in the end? And I'll just show you some pictures on the next slide to show you how that works. So what Gauss proved with the central limit theorem was that under certain circumstances, the distribution of the sample mean does become more and more normal as sample size grows. So let's look at this sequence first, going from the original distribution of x up to the distribution of x bar 2. the sides are pressed down a little and the middle is pressed up a little bit, so you start to get a lump forming in the middle. And then as you go to an even larger sample, so you're doing x bar 4, sample mean for samples of size 4, the middle is promoted even more, the sides are pressed down even more. If you get to 16, there's just a little bit of lump left out on the ends, but pretty much what we have is close to a bell shape in the middle. And then if you go out to about 32, the distribution has become very much like the normal distribution. So what the central limit theorem says, it comes in 3 parts, and if x is any random variable with a given mean and standard deviation, we can say 2 things about the distribution of the sample mean. We can say first that the mean of all the sample means is the same as the mean of the original variable. Second, the standard deviation of the sample means is not the same as the standard deviation of the original variable. It's smaller, and you get it by dividing by the square root of n. If x starts out normal in the first place, then as you go down the larger and larger sample means, they all remain normal all the way down. So if you start out normal, it stays normal. But then if you don't start out normal, still, as the sample size grows larger, the distribution approaches the normal distribution. And for even the worst kind of starting distributions, ones that are extremely bimodal, according to both Triola and also the other author, Moore, they both agree that somewhere around 30 or 32, it seems like there's no noticeable difference between the distribution of the sample mean and the normal. So Gauss's theorem, he only proved that just the bigger the sample is, the more normal the distribution of the sample mean. He just proved it heads that direction, the bigger n gets. But as a practical matter, it seems like 30 or 32 is good enough. So that's it. That's all for this topic, and next topics coming up, we'll apply this to figure out how to do margins of error, how to figure out, is it likely that the sample mean you got for your project might be close to the true mean. That's it.